What is your advice for young entrepreneurs, scientists, and researchers?
Follow your passion, and even if you fail doing something, you will have a lot of learnings from that,
Hmm.
uh, and that will define the path for you as well. That is one aspect.
So, what is the specific problem that Oxen's lab is solving?
Okay, so Oxense Lab, what we are developing now, we have a new kind of RF sensor. So the conventional RF sensor would be an antenna.
And right from founding Oxen's lab to, developing the whole soul product. Can you talk about your journey?
I had a rather unconventional journey. It's not like I started with my engineering. I was passionate about computer engineering, and so I left for kind of ran away from home for Madras.
Mhm.
And so it all started with a fascination for robotics after watching a movie. It's called Short Circuit.
Are you open to collaboration? And if yes, how should one contact you?
Yes, very much. As I told you before, we have a company for defense and we wanted collaboration with multiple research institutions. And so we are bifurcating this one into the civilian applications as well.
Hi, welcome to another episode of Swaraj Silicon. This is our episode number 4, and I'm your host, Poonam Gupta. We are shooting this podcast just a day before Diwali, so a very happy Diwali to all of you. Today, we are joined by someone whose work is at the intersection of imaging, sensing, and computation. Of course, innovation as well. He is Naveen, a co-founder of Augsense Lab, and we are going to talk about his journey. Welcome, Naveen, for joining this podcast.
Thank you, Poonam. Happy to join you.
Naveen, can you talk about your journey from VTU to Chiba in Japan, and right from founding Oxense Lab to developing the whole soul product? Can you talk about your journey?
Okay. So, first of all, thank you for having me. And also, thank you for noticing us because Oxens Lab is a startup. Nobody else noticed us other than few investors. So, thank you, Poonam, for noticing us.
It's our pleasure.
So, let me start with my journey. So, I had a rather unconventional journey. It's not like I started with my engineering, but it starts a lot sometime, say maybe 10 years before my engineering.
Mhm,
So after my plus two, my father was insisting on getting into civil engineering,
mhm,
and I was passionate about computer engineering, and so I left for kind of ran away from home for Madras, pursued AMI in computer engineering. That was something that they started at that time.
mhm, mhm.
And so it all started with a fascination for robotics after watching a movie. This movie used to come on the DD in parts every Saturday. It's called Short Circuit. The
I
Short
see.
Circuit is a movie on a robo
Mhm,
called Number Five that becomes conscious. And the fascination started with that. I wanted to do something in computer engineering at that time, and I left for with very little money from my grandpa. I left for Madras, and then later I realized that you cannot very easily make conscious machines like how they show in the movie.
mhm,
It was all hidden behind a lightning strike on the robo, and it becomes conscious.
mhm,
So they conveniently hit the trick.
mhm,
And so I was naive in that sense, but then soon realized that okay, how much of a complex circuitous path an electron takes in a microprocessor, it cannot become conscious. So there's more to it. So I got interested in the uh, physics aspect. There is probably a physics beyond what we understand to make. So my path went in that direction as well. I was interested in physics, but then at that time I did not have uh, much earnings. It was beginning the formative years. In a way, I could say that real university for me was the Madras,
Mhm.
uh, where I got. So very soon I got into a programming course, and also um, got into teaching, guiding students, engineering students on their projects. And I so these engineering students, they would have external guides from the industry,
Mhm.
say Vellore Institute of Technology at that time, engineering college, Vellore Engineering College. So I kind of got mentored because I used to spend more time with the industry mentors than the students.
Mhm.
I was lucky in that way. So I started learning. And so in a way, my formal education actually followed whatever I passionately wanted to do. And formalization of that education came later. So one benefit was that I started asking the why question much earlier than the how question. Because when you in an engineering college, you're taught something, the
Mhm.
why does not evolve. The question why doesn't evolve. So that was very useful in building the intuition for engineering in me.
Mhm.
So I could ask the right questions and build things on. So a kind of first principles approach to building things, and so that contributed a lot in my formative years in a way.
Mhm.
So from there, I got a chance to teach kernel mode programming
Mhm.
at ISRO Sriharikota
Oh, very
to
nice.
10 engineers.
Mhm.
And so I was still 12th standard, but this one was very, very flashy on my resume. And then I came back to Kerala. I was sent to Japan from here to a subsidiary of NTT. So
Mhm.
that was the one that gave me an actual break in terms of the monetary aspect. Okay. And I was into embedded system. It was related to kind of robotics. Yasukawa, this one was there. Many kinds of embedded systems. It was a case tool development. So I was exposed to all those. So embedded system and driver development became
Mhm.
my kind of bread and butter for some time. And then I wanted to go back from Japan to India and do my engineering, because now I felt there was a need for a formal education, because I was interested in signal processing, but I wanted to do it in a much more formal manner. And
Mhm.
I had this intuition for all those Fourier transform and all this
Okay.
DSP Manilakis
Mhm.
book by Proakis Manilakis.
Mhm.
Uh, those were books I used to study uh, when I was guided by the mentor uh, at Madras. So he was from
When
Doordarshan.
you didn't do your engineering.
I got into engineering uh, in a very unconventional manner in this sense. It was formalized later. So I benefited out of it. And so it was then after, uh, so that was the first time in Japan. I went back and then got into Ramaya College, which is VTU. Uh, and there I did my telecommunication engineering. So all my classmates were 10 years younger to me. And I was, the teachers or the lecturers aware of my age or slightly. So that was again. So I could look at engineering education both from a student perspective and a teaching perspective. Okay, and so they all knew that, okay, I left my job from Japan and I'm doing this one. So they're all surprised as to, okay, this is a bit different. That was and another thing is, because my education was purpose driven, uh,
Mhm.
there was some expectation in terms of how can I build intuition in all my classes?
Mhm,
So I used to get stuck with my what do you call, says I need to build some intuition.
mhm.
So building, if I don't get that intuition or the why question is not answered, I cannot very easily progress. So academically, that becomes kind of so you cannot perform very well even before the exam. On the eve of exam, you would be thinking this way. So that was, but I enjoyed my course, my engineering course, but I never wanted to do a formal education ever again. By
Right.
then, all this chat GPT is all there, and I can always learn. Continuous learning
Sure,
is feasible now.
sure.
Uh,
Sure.
so after that, I went into medical devices where I got introduced to computer tomography and
Okay.
tomosynthesis. We were doing algorithm development for Japanese companies. I was here on and off on various visits.
Mhm,
That was my few visits before I came this time.
mhm,
And this time was to Sony, where I worked on image sensors.
mhm,
The
mhm,
Sony camera, if you know,
mhm,
the image sensors, the
mhm,
pipeline for that,
mhm,
worked on that.
mhm,
So all those got into the sensing aspect of robotics. Again, robotics was there
mhm,
in the Sony
mhm,
as well, machine learning and robotics.
mhm, mhm,
And okay, so from Sony, I went into a robotics company, an aerial robotics company
mhm, mhm,
uh, called Autonomous Control Systems Lab. And there I was working on the
mhm,
perception and guidance for aerial drones.
mhm,
It was a kind of security drone. Uh, Secom is a company that works on security drones all over the world. Drones were introduced by them. So again, sensing, and so I wanted to do something on RF side at that time, RF sensing more than image sensing, RF side, because
oh,
image sensing was very common. There was no, I mean, we were just progressing on that. It was more on how you extract the data from
mhm,
it more than the sensing aspect.
mhm, mhm,
So, of course, there were a lot of other research on the periphery of image sensing,
mhm,
but then RF meant more. It could sense what was not visible. Okay,
mhm.
so I started working on radars, various kinds of radars for sensing,
Very nice.
and it was after this one I got we started Augsense Lab when I was still in Japan. We started
Mhm,
Augsense Lab. I'm still in Japan. I'm based out of Japan.
mhm, mhm,
So when we started, we had this experience of service industry, the software service industry,
mhm,
and the service industry. We thought we wanted to make a difference in terms of a research as a service,
okay.
uh, forging ties with various companies for core research, where the
Mhm,
IP is protected. So one thing
yeah.
that we observed, especially in India, especially in Kerala, um, the Technopark, uh,
Mhm,
I would say, most of the companies in India, service companies, they have software division or R&D divisions within the organization. But these are mostly to give a flavor to the core, non-core work that you bring, because that is the volume is what brings in
yeah.
that is the value. So so we thought we wanted to make a difference, and in a way we could say that IP, most of my algorithm work which could have gotten IP, was actually either a feasibility study or a deliverable of an of a implementation which got used, and they were making money. And I even saw some of uh, our IPs being used in various other companies given by this. So we thought we want to build a sovereign IP, uh, and why not build a research? So then from then on, we also started noticing that there were a lot of research parks coming up. By then, we thought NASCOM is also going in that direction of promoting or add value to the software services. So we thought that is the right time.
Hmm.
And and uh, at that time, we also got a project from Weather News, which is a weather forecasting company.
Okay.
Project in the sense a co-research.
Hmm.
This one. So we grabbed that opportunity, set up a team, and that actually got us started.
Hmm.
So we started off as a research company, co-research, this one. And I was working. Currently, I'm associated with the research and development division of Location Mind,
Hmm.
and I'm the CTO of Augsense Lab, both together, because we are trying to collaborate. Uh, so Augsense Lab is going to have a joint venture uh, in the future, once we have the funds ready. So that is how I'm still in Japan, and we want to take that forward.
So,
That is my journey.
sure.
Okay.
Thank you. Thank you for walking us. I just want to understand what is location mind, which is
Okay.
very specific to
So,
Japan, I believe.
so Location Mind is a geospatial intelligence company,
Hmm.
and uh, it rose to fame, especially during the COVID, because
Hmm.
during COVID, people flow, that is, using GPS location of people,
Hmm.
they could identify
Sure.
where the infection is spreading and things like that. What
Hmm.
are the routes followed? So this had a lot of, that was one of the major impact. Location Mind is a startup at that time, spun off from a Tokyo University lab called Shibasaki Lab. Shibasaki Sensei. Sensei means professor.
Hmm.
Professor Shibasaki was heading this one, and he is a CTO of Location Mind as well.
I see.
He is interested in our atomic receiver that we are developing, because it has got a lot of applications in geospatial intelligence.
Hmm.
And so, in a way, he was also, uh, initially, he was a bit skeptic, but uh, he found that Oxen's lab is taking a very good direction. So
Hmm.
I used to keep him updated, and I think things were very at that time, at a very nascent stage. So rightly so, and now he has picked up interest, and he is promoting me to write a lot of proposals with the JAXA, and so that way we benefit, and we thought we let's have a joint venture here. So that is how I'm still in Japan and managing this. So
Sure.
there's a freedom to uh, go to India and back, and uh,
Okay.
yeah,
Okay.
there's a lot of convenience there.
So, what is a specific problem that Oxense Lab is solving, which is global in nature? And
Okay.
uh, yeah, what is the advantage of Oxense Lab?
Okay, so Oxen's Lab, I will cover the journey of Oxen's Lab a little later.
Sure.
Maybe to start with, what we are developing now, um, we have a new kind of RF sensor.
Okay.
So the conventional RF sensor would be an antenna,
Mm-hmm.
and the antennas, they work on a different principle where spatial change in the electric field is measured.
Mm-hmm. Mm-hmm.
Here, it is the time-based change that is measured. So
Okay.
when you have a spatial change that is measured, you need large structures, large resonance structures to uh, detect a signal.
Sure.
So, for example, at low frequencies, you need very, very large antennas. So you forget about antenna arrays. If you form an antenna array, it will take a whole football stadium. So our problem was, first of all, our problem was to reduce the size of the antenna, especially for low
Sure.
frequency.
Mm-hmm.
And a lot of low frequency sensors were kind of overlooked, because uh, there were feasibility problems using the conventional technique.
Mm-hmm.
The other part is the sensitivity that we
Hmm.
talk about. There's a theoretically sensitivity can be increased to drastically, especially for high wide bandwidth signals. The sensitivity is much better than conventional antennas, and there is no restriction on the. So this can scan from DC to terahertz using the
Oh,
single sensor.
wow.
So usually when you go for an antenna, for
Hmm.
every frequency band you require different antennas.
Sure.
And each of those developments would go through a development engineering cycle,
Hmm.
a lot of refinement, fine tuning. It's a lot of work.
Hmm.
And now we are talking about a sensor that can sense from DC to terahertz. Okay. And without an antenna, that itself is a sensor. There's no down conversion electronics or any
Hmm.
of that sort. So now what happens is, if you can launch such a receiver into an orbit, let's say,
Hmm.
and that is after post launch, you can reconfigure it to use it as a remote sensing. Different kinds of modalities of remote sensing.
Okay.
For example, radio occultation is one such modality.
Hmm.
Electronics intelligence gathering is another modality. Radiometer is another modality. All
Hmm.
these can be done post launch. So the whole economics of space changes, because
Hmm.
the usual practice is you have a mission planned and then get into your engineering aspect. This is like a software defined or
Got it.
reconfigurable
SDR.
hardware up there, which changes the whole economics of space based assets. So that is so. For example, something that a weather company is not well funded in India,
Hmm.
especially to have a satellite of their own. But now imagine you have these satellites,
Hmm. Hmm.
and during peacetime you're operating this one, and in wartime you switch the software to
Hmm.
do something else.
Hmm.
So the whole economics changes.
Hmm. Hmm.
So you'll be able to fund even weather companies. I think we should not ignore the weather company, because there's a lot that can happen, or the national security is dependent on weather, which
Sure.
most countries ignore, and that is where we change the whole game.
Sure. Sure. What is the
Okay.
cost delta versus conventional sensor? What
Okay.
what do you think the cost difference would be?
Okay, so currently when we are playing with we won the IDEX challenge, that was into electronic intelligence. So when we play that game in the defense, we get funded in a slightly different manner,
Hmm.
especially the initial research and in initial products would be, the cost would be slightly different. It can be more because it is in the research phase. And like how internet came out, DARPA funded it, and then everybody started using it.
Hmm.
So it would be the similar journey. So at the moment, the lasers are very expensive. So atomic receiver, it uses a vapor cell with rubidium atoms and various kinds of lasers. Ultra low width lasers are used. These
Hmm.
are very expensive. They have to be imported.
Hmm.
And if even if it is important, when it comes through various supply chain routes, going to from Japan, sometimes it is
Hmm.
going to Europe, and then from Europe it comes here. The
Hmm.
whole cost increases fourfold.
Hmm. Hmm.
Okay, so there is a need for um, these components to be made in India.
Hmm.
These lasers, tunable lasers,
Hmm.
especially for quantum sensing. These
Hmm.
are currently mostly outside.
Hmm.
So the delta that you talked about, the cost advantage initially, this is going to be expensive, but it can be used in niche areas in defense initially, and um, and as I said, the uh, multi-mission satellites, if you launch, you get the cost. So the cost of the receiver itself might be high, But when you look at the mission cost, the total mission cost of launching multiple constellations, that offsets it drastically. So that is where we play.
Sure. Yeah.
Okay.
Makes sense. And then, in simple terms, can you explain what are the new sensing modalities that you talked about and the inverse problems that you are
Okay.
trying to resolve?
Okay. So what we mean by inverse problem is, say for example, if you've heard of computer tomography, um,
Mhm. Mhm.
so computer tomography is like you take X-ray projections. Only 2D projections are taken
Mhm.
from all angles around you, and then you reconstruct the 3D structure, the tissues in the body. You're able to reconstruct it based on only the projections, only the 2D projections. So
Reversibly.
something similar can be done. So this is an inverse problem. A machine learning is an inverse problem. Machine
Got it.
learning is like you you have an input and an output. You're training using input and output. You're training the function that it has to learn to get that output. So it is learning that function. So similarly, over here, you're trying to learn, or you have algebraic techniques. Linear algebra can be used to reconstruct the 2D projection or 3D from the 2D. So
Mhm.
similar is the case with atmosphere also. You have a lot of signals passing through the atmosphere.
Mhm.
And especially now, never before in history has Earth been surrounded by so many satellites that are communicating 24/7, like the Starlink,
Mm.
OneWeb, all those satellite internet satellites, they're
Mm.
transmitting all through the day, both spatially, all globally, as well as in time, because it has to provide internet 24/7.
Mhm.
So these signals are signals of opportunity that you can use to reconstruct. That is, you're getting a projection, signals that you receive, and it is being um, perturbed by the atmosphere in some manner, leading to various kinds of delays. And
Mhm.
using these delays that you measure, you
Mhm.
kind of reconstruct the whole atmosphere.
Mm. Mhm.
The temperature, the relative humidity, the pressure, these are reconstructed. And because these are passive signals, you can also identify where clear air turbulences happen. Clear air turbulences are turbulences which cannot be detected by radars
Okay.
because it doesn't give you a backscatter, a very feeble backscatter that you cannot detect.
Mhm. Mhm.
So, clear air turbulence is something that you experience when you go on a flight and all of a sudden there's an air pocket. That air pocket can be due to clear air turbulence or other turbulences as well. But this cannot be detected. There's no warning system for that. And this is a huge problem, especially with increasing extreme weather. Extreme weather, every year it is the number of incidents are increasing.
Mhm.
So we thought that would be one of a major. So we have a patent. We are granted a patent on clear air turbulence, but it is only now we are connecting the atomic receiver part to it, which is a very sensitive sensor, which adds value. So
So,
weather sensing is one area. Defense is definitely another area. Okay, so on the modalities that we talk about, there's
mm,
another modality called radio occultation,
mhm.
which when it came in with the mission called Cosmic and Cosmic 2, it had an orbital shift in the forecasting skill just because of these satellites, which was doing radio occultation. So radio occultation again is signals from GNSS satellites are
Mhm.
captured, they propagate through the atmosphere and captured by another satellite, which is maybe in the LEO. And um, so Spire is doing it. There are multiple companies, and so when they started doing this one, there was a drastic shift in the weather forecasting skill, um, and now we think this sensor, because our atomic sensor is a little different and with high fidelity signal detection is feasible. And so this will make yet another orbital shift in weather forecasting. So I'm comparing that to what Cosmic and Cosmic 2 brought in. So we are going to make another shift. And also, as I told you, okay, uh, so on the modalities aspect, the radio occultation, and so we started off with conventional systems initially. So we also have a ground penetrating radar. We started off with conventional ground penetrating radar, and anybody developing ground penetrating radars world over would know what is the pain in detecting objects clearly, because there is actually a feasibility problem in detecting with high resolution using conventional system, because only at low frequencies you have the signal going through or penetrating the soil and the regolith. And at low frequency, if you choose to increase the bandwidth, then the bandwidth is, say, for example, 1 gigahertz bandwidth, it
Mm-hmm.
goes beyond uh, the the high frequencies will not penetrate. So within the bandwidth itself, it will not penetrate the
Mm-hmm.
soil enough so as to
Mm-hmm.
have a high resolution imaging.
Mm-hmm.
So this changes the whole game of subsurface imaging, which is especially needed in Japan. That is one of our collaborations,
Mm-hmm.
where it is very disaster prone, earthquake, detecting people under the rubbles. So that is one modality that we're working on.
Mm-hmm.
We have surrounding us, there are basically even synthetic aperture radar. GPR is can be equated with a synthetic aperture radar because
Mm-hmm.
we are doing it in a slightly different manner. It can be used as a synthetic aperture radar from drones, and so that is one aspect. So I talked about synthetic aperture radar and the GPR in one single uh, modality. The radio occultation was another one. So uh, related to radio occultation, there's reflectometry,
Mm-hmm.
radio reflectometry. That is another one. And so ELINT, I also talked about ELINT. So basically, we are focusing across these modalities. You would notice one thing, that is, when a signal is becoming weak, either through propagation through the atmosphere or through propagation into the subsurface, the soil.
Mm-hmm.
Um, and so these are the modalities that we have chosen because atomic receiver makes a difference here. It the uh, the idea is to differentiate the initial development of atomic receiver with a very niche example to show that there are modalities that cannot work using conventional antennas, which can work here. So
Mm-hmm.
that is the niche area that we are focusing. So that is how these four modalities are chosen. I think to answer the question on modalities and the inverse problem, so there is a relation between most of the modalities. Say, for example, radio occultation.
Mm-hmm.
These are again signals that you receive on the ground or on the satellite, that
Mm-hmm.
these are inverted to reconstruct the atmosphere. The the other could be ground penetrating radar or synthetic aperture radar.
Mm-hmm.
Synthetic aperture radar usually is used only for surface based imaging. But here we make a difference when you're able to image the um, layers underneath
Okay.
uh, within the regolith. You can image the layers,
I see.
so that makes a difference. Uh, that is one aspect that
Sure.
we bring in. So
Sure.
over there also inverse problem is involved.
Mm-hmm.
Okay,
Mm-hmm.
I think I covered all the four modalities that we are currently focusing. Yeah.
So do you have to maintain any specific temperature? Like for quantum sensor, you have to maintain it ultra cool. So you have to
Uh,
maintain all that.
so
And
the
is it
technique
really
that we
difficult?
use is called it is room temperature based.
Okay.
So you can achieve um, room temperature. So this is based on something called a Rydberg atom. Rydberg state is like an atom that is excited to a very high state. The electron is very much removed from the nucleus, and it's a very big atom. So, and these are achieved at room temperatures. So you also need a vapor pressure to be in the vapor cell. So you can make use of room temperature, and the sensitivity is uh, unlike the kind of cryogenic environment that you use in cold atom interferometry and things like that.
Mhm.
We don't need it here, and that is what makes it feasible out in a field prototype. For example, the cold atom interferometry, you cannot have it probably outside. It's very difficult
Sure.
to have all the, and the size, weight, and power
Mm.
uh, cannot be that easily used outside. So we are focusing on only on this one, and
Sure.
this is a ensemble based technique, so it works.
Mm.
We're able to
Okay.
detect
So there is no trade-off in the accuracy.
the accuracy or the sensitivity of the atomic receiver. There are various kinds of technical noises that are involved, like the laser itself. You cannot have a ultra uh, narrow line width lasers, and especially when it is on a platform that is shaking, it will add a lot of other noises. So basically, we have removed the solid state noise. Solid state, when you're using, you have the noise due to the KTB noise. There's a frequency bandwidth dependent noise. Those things we are not using because it is a atom in the vapor.
Hmm.
Atom.
Got it.
So solid state noise is removed.
Hmm.
So that itself gives us a very good advantage in
Sure.
terms of frequency independent or bandwidth independent
Hmm.
noise. We only have the technical noise due to the lasers. So that is one advantage there.
Hmm. Hmm.
Yeah.
And it's not easy to navigate from lab to a product development. What are
Right.
the kind of hurdles that you faced and how did you overcome those?
Okay. So the development started off with optical table in the lab. Most of the POCs were done over there.
Hmm.
And we initially itself we understood that solving the supply chain issue is a major problem
Hmm.
because India doesn't have most of these components, be it lasers, be it vapor cells, MEMS based vapor cells. These are all at very nascent stage or not there. So we have to work towards, we should have a plan that is a long term for a sovereign fabrication with a foundry that can fabricate this one,
Mhm.
uh, and parallelly take it to a commercialization by collaborating with various universities. Say, for example, in Japan, we are trying to collaborate.
Mhm. Mhm.
So we need a two parallel path. One is to build a sovereign facility to do it in India, so that you can uh, build it for defense and also
Mhm.
later on for commercial applications. But we have this other path when we want to buy these components, MEMS based vapor cells or lasers. Say, for example, Nichia Corporation is in Japan. They
Mhm.
have the blue lasers. They are the manufacturers of blue lasers world over. Everybody buys it from them. And so these components will have to be sourced. To develop the field prototype, especially in India, we had a lot of hurdles. Because we are working in the defense sector, we have to bifurcate the company into two. Okay, one so that we can have the sovereign manufacturing and foundry setup, and
Mhm.
this can go into the defense. The
Mhm.
other one, we separated out the civil. Very soon we'll have two companies that will take care of the research and collaborations with for non-defense aspect.
Hmm.
So that we have a lot more commercialization
Hmm.
that can be done early on. Use components that can be used.
Hmm.
That is how we are planning.
Hmm.
So yeah. So when it comes to developing, so the developing a product that can go into the field, uh, it is under development now with a lot of iterations because, as you know, quantum sensing has its own challenges. The physics, every day we find something comes up and that has to be solved. So it's a kind of tentacles, problems multiply, but we
Very
also converge. Yeah, start converging. So it is interesting. We get exposed to very multidisciplinary areas, and be it optoelectronics, the control system for the lasers. So gradually, we are getting into this one. So our initial prototype would be a prototype that uses only micro optics, doesn't use semiconductor.
okay.
And it showcases only a minimal set of an
Hmm.
array of RF sensors and it can be used in various kinds of modalities in a commercial manner. But the long term goal that we are working on is so we've designed all those photonics integrated chip based implementation for
Sure.
developing atomic receivers.
Hmm.
And our labs, say for example, CPICs at IIT Madras, they have um, a lot of these PDKs, the components that we want, but
Sure.
not all of them, or the
Hmm.
things that. So over there, if you are doing it, it'll take some time. So India is still at the nascent stage of developing all these components so that we can readily use. So,
Hmm.
which is why we are planning to also have um, options outside India.
Hmm.
Uh, we can make use of many fabs, especially in Europe, that can you can have a multi-project with
Hmm.
runs over there and do it at very low cost. That is a plan. But longer term, we should have our own foundry because a lot of these customizations that we require are not available, and if that has to be done, that that has its own challenges in navigating it with a university and
It will be
uh,
costly as well, I believe.
yes.
Hmm.
As you know, even working within India
Hmm.
with a lab who
Hmm.
might have uh, um, who might have all these facilities that we can use, but a professor working there might be engaged in something else, and they don't have the resources to share it with us, or there
Hmm.
could be various other policy hurdles that. So
Hmm.
we thought we will invest in our own lab. So we set up our lab.
Hmm.
So that is where Solar Industries is one of our investors.
Hmm.
Our first investor who noticed us and kind of strategically positioned themselves for the long term. So
Hmm.
they invested in the lab. Uh, yeah, we invested. Uh, they were the first investors, and that brought us. We were able to continue the journey a lot more, but we need more funds. So and we need risk averse people to fund it.
Yeah,
Okay.
somebody who understands the
Yes.
nitty-gritties of this ecosystem, right?
Right.
Especially in space.
So, especially in the deep tech, uh,
Mm.
India, because of ISRO's presence, there is a lot more. The funds are forthcoming in the space sector, but
Mm.
not many in the sensing or the semiconductor related areas.
Mm.
Uh, Netra Semi definitely they form a very good example. Yeah, funds coming through in India. We cannot strategize or anything. It is you meet a lot of investors and over the period they get convinced. Once you seed this thought, they might come back later, and Many times that happens, and
Mhm.
then they get interested. The first time it is not. So,
Mhm. Mhm.
and many might be even skeptical that this can be done in India because we don't have all those facilities that we require. And so the question would be, are you the right team to do this?
Mhm.
Okay, so yeah, so as I said, um, I don't have a formal education or the pedigree that I from IITs or IISCs, but I surround myself with all these people. So, did I deviate a lot from your question? Your question was, uh, what what is the challenge in developing a field prototype and converting that into a product,
Product. No,
right?
no, no, absolutely not. And that brings us to the next question that how do you see India's deep tech ecosystem evolving since you have worked across Japan and India? And what do you see still is the gap, like in terms of investment, talent, or some kind of partnership, or in terms of infrastructure?
Okay. So one advantage I see in Japan is
Mm.
that the funds, one is it is huge,
Mhm.
uh, and when you write the proposals, these proposals, so there are multiple projects. They have a fund for a particular theme, and there are multiple projects that would be allocated, and that is allocated in time. There is a fixed time in which it is evaluated, and you're able to plan across these deadlines. And because there is not so many applying for it, it is easier to get those. Unlike in India, there is 1.4 billion people, and not everybody trying to grab a piece of uh, these funds. So we have that disadvantage because anything innovative is a no, because there is a uncertainty around it. Whereas in Japan or most of the developed countries, you when you allocated a fund, it is because of the innovation factor is the major element for which you get the fund. But that is not the case in India, because you have to uh, you
It
cannot
is
waste money
inversely
there.
proportional.
Yes, you cannot waste money, so, and especially when so many are looking for, can you build something more tangible,
So
so
true.
that is a problem that
So true.
we face, especially in India. And so most of the projects, for example, be it IDEX or any of the proposals, these are all the deliverables.
Mm.
It is not, even if it is an innovation fund, it is considered as a project when you will
Yes.
deliver for sure. Okay.
So true.
So everything is beyond TRL 6, technology readiness
Ah.
level 6. Okay, so it has to be innovative. At the same time, it has to be TRL 6. So what is the need for funding then? So,
Yeah, yeah.
so that is a problem we face. It's because purely because of the population that we have and the funds that are scarce.
No, it's also because of the mindset. I mean, the mindset is like that, right? So the
Uh,
mindset needs to be changed with respect to innovation. This is what my
Innovation. Yes.
opinion is, personal opinion.
Yes. The mindset has to change in terms of, so one is educating, say for example, somebody who is innovating or starting a company in US and fails, they still wear it as a badge of honor.
Mm.
But
Mm.
in India, not the case. Somebody who has a startup and it fails, it is not considered as a contribution, or they took the risk to build something new but uh, failed, but it leads to something else.
Mhm.
But
Mhm.
maybe the kind of generation that we live in, the parents are not very supportive of these aspects. So
Mhm.
that purely because of the kind of economics or the we have in India. So
Sure.
developed countries, yeah, especially US, Japan, Europe, the kind of funds that we get, Indians probably should go for joint ventures elsewhere to fund themselves, and also have a sovereign plan also for the
Mhm.
long term. So I would say deep tech really needs fund from outside, especially when you want to take risk. You
Mhm.
need fund from outside because things are changing in India. I do see a lot more fund coming through, making larger funds and taking more risk.
Mhm.
Maybe the geopolitics also contributes a lot in
Yes.
terms of, okay, let's make it here itself. So we are living in a good time in that sense.
Yes, certainly, certainly. And you were also invited from PMO, I mean, Modi's office, right, in Japan.
Uh,
And it is considered to be a greatest honor, right?
yeah, that
So,
was yeah.
did you see any impact of that? And has your vision changed since then,
Okay, so taking a picture with two
Mr. President?
PMs,
Uh,
uh, Prime Minister Modi and Shiba, that it is like there was no interaction whatsoever with, uh, but the valuation increased, 10x, 100x. I don't know. We got a lot of call from the defense. Many people uh, contacted us, and we yeah, people started noticing us. The best thing was maybe our space sector. This was on a very short notice.
mhm.
That initially the plan was probably December, and on August 29th, because the geopolitical situation came
Okay,
a little more early, I guess.
I see.
And so a lot of the space startups who would have otherwise come to
Mhm.
frequent here, they did not appear. I don't know. It planning was done not. There was no very little time to plan. So
Mhm.
I had an advantage there because I was already in Japan, and
Uh,
Location Mind was already signing an MOU. I
mm,
went through METI, and
mm,
uh, METI called us.
uh,
METI is a organization.
mhm,
So uh, that was a very good opportunity for us in that sense.
mhm, mhm,
But don't I wouldn't say that because we were so very good a company and we were selected by the PMO that we appeared there. No, that's not the case.
That's
There
your
are far
humbleness.
better companies probably, but we are definitely good in nobody noticed us. So that was an opportunity. That's how I see it.
No, you are humble to say that. Anyhow, uh,
Thank you.
what is your advice for young entrepreneurs, scientists, and researchers, upcoming generation, for to develop such products? What advice do you want to give to them?
Okay, I think I benefited surely from the unconventional education that I had. That is, the
Mhm,
degrees should come later. Follow your passion, and even if you fail doing something, you will have a lot of learnings from that,
mhm,
uh, and that will define the path for you as well. That is one aspect. Most of the one thing that I've noticed, especially among um, IITians and the premier institutes,
mhm,
because they follow a path which is well trodden path and there's no risk involved. uh, Many tend to believe that it is better to go abroad, settle down in some job, and take a very less risky path.
mhm,
So that is also because the funds, as I said before, uh,
mhm,
that has to somewhere change, in the sense that if you start building intuitions and uh, for example, what I mean by intuition is, in most cases, there's a lot of math that is involved, which is not intuitive, and so you're not able to apply. And focusing on building that intuition helps in building very good products. And it will also not just products, it even the ecosystem of products that you want to build, that helps.
Mm,
How to ask the questions from first principles, challenge it, and those are the ones that go very long way. So if you're uh, spending your time trying to write exams, and uh, in that you don't really get the time to have a build intuition. For example, you see an equation, you see a final, after deriving all those expression that you get, looking at it, can you make sense of it intuitively, uh, say how this is coming.
mm,
For me, from the beginning, I was exposed to thinking in those levels because I did not have a formal education. Looking at an expression, final expression, I would try to understand what are the ingredients and try to make intuitive sense. And that goes a lot of far into making or applying this one elsewhere.
mm,
So, and in most cases, our exam systems are very much compartmentalizing the subjects, that you do not dare to think relations between two subjects.
mm,
So I think when they are not put in an education system, and you learn from ChatGPT, you tend to do much better. So I think the current generation should use ChatGPT for their learning and ask questions the questioning way.
uh,
It was much difficult at that time. See, no
yes.
longer universities or IITs have this advantage of having all the literature available there. It is
Mm,
available on the internet everywhere now. So
mm,
that those were the days. Those systems have gone. So now you need to get into ChatGPT and learn. Forget about uh, the kind of formalized degrees, or maybe it'll automatically happen. Shorter nano degrees will start forming. But I think India has to introduce this one, nano degrees.
certainly.
Just do this one, get into the job, learn on the job, collaborate and learn. So that system, if it comes, it can make a big difference in India.
Certainly. Certainly. And Naveen, just the last question. Are you open to collaboration? And if yes, how should one contact you?
Yes, very much. So, as I told you before, we have a company for defense, and we wanted collaboration with multiple research institutions.
Mm,
And so we are bifurcating this one into the civilian
mm,
applications as well.
mm,
And we want to grow very fast. So collaboration is the only way to do that.
mm,
Not just in India, outside India as well. Japan is one area that we're looking at, Europe.
mm.
Uh, yeah, so we are open to collaboration in whatever manner. Um, it all depends on how we interact. Uh, yeah, everything comes from that. Uh, so we might take an approach when we might not be open to all collaborations because there are things that we prioritize.
Certainly.
So yeah, so definitely I'm open to. So if through this uh, interview I'm getting a lot of uh, collaboration, uh, if they reach out to me, good. Thank you, Poonam, for this.
Then I'll charge you a commission.
Okay.
No, that is lovely. Thank you, Naveen, for giving us your perspectives on the deep tech ecosystem and how India has to evolve. Thank you so very much. If you like our journey, Please do follow us. And thank you.
Definitely. Thank you.